Hello, I'm Dr. Miller. I have been studying a new way to learn math. It has allowed me to understand math far better than I had ever dreamed I could. So let us begin by looking at what I've been working on. So basically, what I found by using a vector model for mathematics, I'm able to see things in a way that's different than I've seen them before. So let's begin to see how we get started. Is math founded upon interpretations that are not rigorously challenged? There are many misconceptions and anomalies that can be explained by a more rigorous interpretation. Zero being considered nothing, negative numbers not being counting numbers, addition and multiplication being considered commutative, a line not having sides, an area not being negative, are just a few examples of interpretations that I feel should be reconsidered. In fact, take a look at this thermometer over here. We're told that zero is nothing. Here I have a zero in centigrade, and I have a zero here in Fahrenheit. Which one is nothing? If I pick the one in Fahrenheit, then zero is really approximately minus 20 degrees. If I pick the one in centigrade, then zero is approximately 32 degrees. We do have something called absolute zero. That may be a definition that people are talking about. But if we look at absolute zero, there are no negative numbers. So when I start applying to math to some of the everyday things that I see, it starts not making sense to me. So the first thing I did was try to get myself organized in just elementary mathematics. And what I've done is taken the three basic operations. I believe exponentiation should be taught in the grade school. And you'll notice that each one has an inverse. I'm beginning to give some structure and organization to the map. Geometry works its way into algebraic math through the concepts of translation, scaling, and rotation. I began to discover that I didn't understand what size meant. If I took half of something, if it was a large object, I got a large half. If it was a small object, I got a small half. Even with measurement, which we get to at this point down here. Let me just skip to that. What is length? If I put up a ruler and I measure something in the United States and it's 2 inches, I would associate two with that measurement. But a Frenchman would associate five with it, 5 inches. These were things that started making me think. And then I looked at something else interesting. What resulted when we got to the inverses? What resulted for addition was we found negative numbers or subtraction. For multiplication, we found fractions, and explanation, we had irrational numbers. Starting to put things together for me. And then there were special numbers. Zero, the identity element for addition. One, the identity element for multiplication. And I, the so-called imaginary number, has to do with rotation. And if we were looking again, these are geometry. Addition seems to be referring to points, multiplication to lengths, and exponents to angles. And here's where the vectors come in. First, we have a position of the tail end of the vector. Then we have a magnitude, whatever that is, which basically is the size of the vector. And then we have direction. So as an example, if I have a negative number, the minus sign is really direction. And the length of that vector is the magnitude. So what we're going to discover is these simple little things which I brought up, which have asked me questions. We're going to see how I learned to answer them and maybe how you'll learn to answer them. So the first concept we come with, my favorite one, zero is the start of the positive and negative numbers. Has no magnitude and is represented by a dot with vectors going in the opposite directions. We have this little example here. This interpretation plays that minus zero and plus zero occupy the same point. Since zero has no magnitude, This becomes a definition of a point in geometry. So right now we're starting to deviate. We're telling that 0 has signs. If we use the function 1 over x, when x is equal to 0 as an illustration of this interpretation, since it's 0, at minus 0, we have minus infinity, and at plus 0, we have plus infinity. In computer printouts, a number very close to 0 is written as minus 0, and on the left side, and a plus 0 on the right side. This is starting to give me an explanation that's contrary to what I've been taught. According to a Google search, the statement that 0 is nothing is a philosophical interpretation, while the existence of properties of 0 are established within mathematics through a system of axioms. 0 is a core concept that is fundamental to modern mathematics. Yes, 0 often represents nothing as the absence of a quantity like no apples, but is also a vital number in math, acting as a placeholder. And even that I disagree with. So I hope that you can begin to see where my confusion came in. And if you take a look at this in several directions, as I've been showing you with several examples, maybe you'll be convinced that there's a better way to look at 0. Okay, so let's start off with this vector notation. Okay, so with a vector notation, we use a vector pointing in the opposite direction of a positive number to get a negative number. So here's minus 1, minus 2, minus 3, and minus 4. Plus 1, plus 2. If we add 1 to 1, we get 2. If we add minus 1 to minus 1, we get minus 2. Minus 1 again, minus 3, or minus 2. We can see the vectors doing that for us. And so now it becomes obvious to us why we add negative numbers like we add positive numbers. We just put a direction in front of the minus sign. And look at this. I take 2 and I add to it 3. So when I get to this end, instead of moving in this direction, I'm now moving back. And it's obvious I have 2 negatives left over. So 2 plus minus 4 is minus 2. Makes it easy to see this. Okay, so now we're beginning to get the rules. And another rule which we observe from this is that if we take the negative of a positive number, we just change its direction. We take the negative of a negative number, we just change its direction. This made it really easy for me to understand what was going on. But let's look at it from a more algebraic approach. The concept is an interpretation, so later we will produce examples with multiplication to illustrate that it is consistent with our knowledge of mathematics. Let's look at some proofs. If we add a negative number to a positive number, which we can see on our vector diagram, we are back at the starting point, 0. If we just use mirror instructions, if we bring the minus 2 over the other side, that's a subtraction, and 0 minus minus 2 is plus 2. The minus sign changed direction. Or if we have minus 2, we subtract 2 from the other side, and this actually defines the notation. We just drop the 0 and move the sign up a little bit. And here's some other interesting things. We know that 0 plus 0 is equal to 0. So then 0 is equal to 0 minus 0. Instead of using the number 0, let me use another number. Minus 2 is equal to 0 minus 2. All I'm doing is replacing the 2 with a 0, and I get negative 0 is equal to 0 minus 0. So I can interpret this, subtracting a number from itself gives me 0, plus 0. Subtracting a number from itself, from 0, gives me a negative number. So this expression can be either plus or minus 0. Alone, it leaves us with a little bit of doubt. But when we see this coming in 2 different directions, it makes us more confident that 0 has a sign. Another way of looking at this, here is our number line. I don't know what these numbers are here, so I'll just call them A and B. But I know how I create my numbers. I add 1 to the previous number. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. Okay, so now B plus 1 must be equal to A. and a plus 1 must be equal to 0. Well, if I now add 1 to both sides here, I get b plus 2 is equal to a plus 1, which I know is equal to 0. So I have a plus 1 is equal to 0, and b plus 2 is equal to 0. Subtract them. I get 0 minus 1, 0 minus 2, and notation-wise, I've learned to write this as minus 1 and minus 2. So what we begin to see in here is if we put these numbers back in these two equations, we get minus 1 plus 1 equals 0, and minus 2 plus 2 equals 0. Now I feel much more comfortable with negative numbers, just by looking at numbers as vectors and looking at it a little bit different than other things. The anomalies have begun to disappear, and I've got contradictory results from what we had before. So now let's look at counting numbers. Remember we said that negative numbers couldn't be counting numbers. We're going to see how this new way of interpretation allows us to make math easier to learn and apply our knowledge. Traditionally, counting numbers are only positive numbers greater than 0. Yet 0 and negative number can be interpreted to be counting numbers. Since multiplication is a counting process, let us look at the impact of negative numbers on multiplication. The expression 3 times 2 can be written as 0 plus 2 plus 2 plus 2. A little bit different than you're used to seeing it. We know that the 0 doesn't change anything, but it's going to change our understanding of what multiplication is. 3 times minus 2 would be 0, and repeat minus 2 3 times. And we know when we add negative numbers, we get a negative number result by just adding the numbers as a positive numbers and putting a sign in front of it. Okay. What happens if we multiply by a negative number? And let's see how the counting process comes in there. Minus 3 times minus 2 would be minus 2 plus minus 2 plus minus 2, and we put a minus sign in front of it. Well, minus 2 plus minus 2 plus minus 2 is equal to minus 2 plus 2. Well, 2 plus 2 plus 2 can be replaced by 6, which is a minus 6, but a minus changes the direction, so it becomes a plus 6. And if we just do it for ordinary numbers, minus 3 times 2, or positive integers, we get 0 minus, and we put a plus in front of the 2's. We get 6, and when we subtract 6 from 0, we get minus 6. So the rules have changed, okay, a lot. We now take a single step to prove something rather than some long approach, which I found has some fallacies or incompletenesses in the approach. This is what started making me feel good about this new approach that I'm showing you. Okay, so now let's look more detail in multiplication. What I've shown you that this is the old way of writing it. This is my way of writing it. Now, when I say my way, there are other people that share this opinion too. Okay, so 2 times 2 is 2 plus 2. All I did was drop a plus 2. 1 times 2 is 2, dropped a plus 2. But when I go to 0, if I don't have any plus 2 to drop. But you say, well, that's no problem. If I throw the 2 away, I have nothing left. Yeah, but you're not obeying the rules. If we do this way, I'm dropping a plus 2, I'm dropping a plus 2, I'm dropping a plus 2. It becomes obvious that 0 times 2 is 0, unless you make a mistake like they did and put a 2 in there. Okay, so when we drop that plus 2, I would be left with a 0. Mistakes may be annoying, but they help us understand things better. In the first example, we keep dropping a plus 2, but in the last step, there was no plus 2 to drop. We also know that 2 times 0 is equal to 0 plus 0, and 0 plus 0 is equal to 0. Or we could have the new way I've done the multiplication as 0 plus 2 zeros, again, is 0. We have just shown that multiplication is commutative with respect to 0 without applying the commutative property. We showed that in the natural process, when we multiply a number times 0, it's obvious that we get a 0. But it's not until we redefine multiplication that it becomes obvious that it should also be 0. And you'll notice the reason why I'm doing this is I want to avoid using the commutative property. Okay, so, and we showed a similar trick with the negative numbers. Okay, now let's continue with multiplication. Okay, and what I was basically showing, which I skipped over there, is that if I do the counting with this before, it's just merely sign changes to tell me what I have. So this negative number being used as a counter, we use it just like a positive number. The only thing is because it was a negative number, we put a minus sign in front of it. For some reason, the mind is able to accept that concept like that fairly easily. And that's where we get into trouble. How do you know that what I've just said to you is not a better way of doing things, just a more confusing? That's for you to decide. Now, we don't want multiplication to be considered commutative or based upon the commutative properties, and we know other examples where it's not commutative. But we do assume that it's distributive. And that means if I multiply 5 times 1, I can write this as, well, starting off, I can write it as 1 plus 1 plus, there's 5 ones, I call that 5. So now I want to multiply 5 times 3. Well, I replace 3 by 3 ones. And then I use the distributive property to multiply by each one. But I know 5 times 1 is 5. Oh, I've got 3 5s there. So this must be 3, 5, 5. I start off with 5 3s. Now I have 3 5s. So the distributive property with integers comes about because of the distributive property. Okay, so now let's show why this was of a concern to us in one example. If I have minus 4 to the first power, I can write 1 as 2 times 1/2. But if I use the rules of exponents, I can square it, which will give me 16, and then take half of that, and I'll get 4. Well, the squaring process made this a positive number. And taking the square root, it could be positive or negative. There was nothing that told me it had to be negative, so I got an answer that was different. But on the other hand, if I take 1/2 first, this becomes 2i, where I is the imaginary number squared root of minus 1, which I showed you in our first slide. I square that, and 2i becomes minus 4. So if I take the fractional part first, I get the right answer. If I take the integer part first, I get a different answer. Yet this would be true for +4. What we want in mathematics is consistency, and where we don't have consistency, we want to be able to explain it. Okay, now, another example where multiplication is not commutative is if I multiply matrices. And here's a matrix 1, 2, 3, 4, multiplied by 5, 6, 7, 8. And the way this works when I multiply them, I take this group, multiply it by this, then take this group and multiply it by this. Take this, multiply it coming down, and take this and multiply by the second one coming down. So you can see how the numbers fit in this starting position is in the corner. And going down, when I slip down here, it goes a line below it. So it is obvious that multiplication is not commutative for matrices. To resolve this anomaly, we make the following definitions. Multiplication is based on the distributive property. Multiplication is not commutative. But if we wanted to qualify it more, we can say it is commutative for integers, positive integers. Okay, this subtle change in f of 0 and negative numbers use many of the anomalies created by former interpretation. Okay, we've been talking about numbers as vectors. Let's get in more into that. We look at more of the anomalies in the current mathematical logic. We begin to realize that we think of numbers as vectors. These anomalies disappear as they did with the concept of minus sign as an indicator of direction rather than magnitude. So here is a vector of magnitude or length A and one of B, and there's an angle theta between them. And when I want to calculate the area of this parallelogram, it's the product of A times B times the cosine, which is how we do multiplication of vectors to find the magnitude. The direction will be another question, which is not relative now. Well, this is not what we think of multiplication. However, if theta is 90 degrees and I get a right angle, now I'm finding the area of a rectangle. And usually when we're dealing with concepts like 90 degrees, we call this orthogonality. And if A and B are equal and 1 unit, whatever 1 unit may be, then we get a unit square, which is what our measure of an area is. Thus, traditional multiplication assumes orthogonality of the width and the length. So we're not really changing much in here. We get a better understanding of why we represent areas by unit rectangles or unit squares rather than parallelograms or triangles. Okay, and then we talk about negative areas. Okay, here is we're sitting on the ground and we dig a hole in the ground. And if we want to find the area of this, what we do is we take this and then subtract it. Well, if we add a negative number, it's the same as subtracting. Now, how will we rationalize this as a negative number? You'll notice that if we go around the outside polygon, we are going around clockwise. If we go around the inner polygon, we're going around counterclockwise. And what we've done is we've gone there, gone down to the center, gone around, and then come back on the same line. So we're not worried about an area of that line. So looking at this way, we can see that how we can define an area as being a negative area. Okay, so this again added more excitement to my discoveries and things when I discovered that I could explain things before or look at them in a different way and understand them. So now we go to fractions. Okay, in fractions, I define a fraction as the fraction is multiplied by its inverse, which is an integer. And so 1/2 times 2 is 2 times 1/2 is 1/2 plus 1/2, and 1/2 plus 1/2 is 1. So notice we're getting that parallelism with addition. So whereas addition is translation, multiplication is magnification. But let's see what that means. This particular square in there is 1/4 of this square here. It's 1/4 of the old, but it's 1/4 of this square. But if this is a whole, it's 1/16. And if we go to this object, it's 1/32. So it takes 6/16 of these to make this whole box, and many more to make this big box here. So again, it depends upon what our reference point is, what we mean by a half. Now, on this next slide, I've made a mistake. This is 1.23. This is 12.3. So I have 1 of these, 2 of these, and 3 of these. The blue squares, when I've gone through what the relationship is. Now let's do this with our numbers. 1/3 is 1. The 0.2 is 2/4 because we're in the base 4 system. And the 3 is 3/16. And when I add these together, I get 27/16. Okay. Now, if we go over here, 12.3, 1 times 4, 2 times 1, plus 3/4. This gives me 27/4. And you'll notice this 1.23 has to be multiplied by the base, which is 4 in this case, to move the decimal point back this direction. So we're getting bases and fractions in at the same time. Maybe a little overwhelming, but it's a trade-off I had to make when I was showing this to you. But if you go back and read it a couple of times, which is the way you're supposed to study, then it becomes more obvious. You'll be glad that I made mistakes so you can show that you understand it better than I do. Okay, complex numbers, I'm just going to touch them surface-wise. But basically with a complex number, if I take the square root of 4, and 4 can be written as minus 2 times minus 2, square root says take one of the identical numbers, and I get minus 2 as the answer. But if I take the square root of minus 4, I can't find two numbers multiplied together that are the same number that will give me a negative number. So I introduce this concept of the square root of minus 1. I happen to have an I in there, another little mistake on my part. Okay, so I times 1 is I, because we multiply. I raised to the first power is 1, because the one, something raised to a power of 1 is itself. But I squared is minus 1. So we're actually defining the square root of minus 1 as the inverse of this operation. I3, we multiply 3 i's together. We already know I squared is minus 1, so this becomes minus I. I4th, we multiply 4 i's, but we multiply them in pairs, so we get minus 1 times minus 1, and 2 minuses is a plus. We can see from the graph and the algebra that every time we multiply by I, we rotate 90 degrees. That's that orthogonality concept coming in again. We also discover independently that e to the I phi power is equal to cosine of phi plus I sine of phi. That takes a little work to get. So let's summarize what we've done. Kurt Gödel's work in logic, especially his incompleteness theorem, proved that any consistent asymptotic system powerful enough for basic arithmetic contains true statements that cannot be proven within that system. This is still true because we still had to observe the distributive property, but we show you have to be very careful that you don't fall into the trap that Gödel has set for us in proving his theorem. The Turing test, posed by Alan Turing, is a benchmark for a machine's ability to exhibit intelligent behavior indistinguishable from humans. Comparing humans to humans, we showed that by using a vector model to interpret mathematics, we could explain the anomalies of mathematics and then using the Turing approach to validate our inferences. So the Turing approach is what kind of questions you ask to distinguish between a machine and a person. What kind of questions you ask to distinguish between to determine whether a person understands something or not. This is not strange. All PhD candidates go through a questioning process before they can show that they understand what they've been taught. Math education can be changed by using this approach to show the fallacies in the existing process, thus making the change seamlessly. Now, I leave that responsibility to you. Thank you very much for listening to what I have to say, and hopefully you have learned as much as I have.